Okay, all right. Good morning, class. Can you guys hear?
Yeah, good morning, sir.
All right, good. So the lesson plan for today is pretty simple. We're just gonna go over screws and pulleys and do pretty much the same thing we did in last week's class. All right. So let's just look at the screw and look at finding velocity ratio for a screw. See, I got a picture here of a screw. So this is what a screw is. However, I think everyone already knows that. Um, So let's look at how we would apply the effort for a screw. Right. So when trying to put the screw, like when trying to lower it maybe into a piece of wood, if it's a very simple screw, or in this case, this block that would be connected to maybe a jack or something, right? And this would try and push up or something like that, right? We find out when we rotate the effort one complete revolution, right? The distance we travel in terms of moving the load is the distance between these threads, right? So this distance p. So when we do one complete revolution, right, applying the effort, the distance we travel is this distance here, p. And that makes sense, right? Because we go around, we screw this thing into the other object or out of the other object, and it travels this distance between the threads. So that's our distance p, right? Now, the effort can, of course, vary depending on the radius of this screw. Or in other cases, maybe it's a bolt, and you would have a wrench or a crescent on it, and the crescent would have a certain, and then you would apply effort along the length of that crescent, right? So that would be the 2 pi L, L that you would want to apply the effort, right? And of course, it's not always like this. It can be in the form of this. This is a car jack. As we can see, the mechanism is similar. It's the same screw, but here we apply the effort with this bar, right? And the radius that we can apply that would vary how we angle this bar and how we pull it around, right? So the radius could change, and it doesn't have to be like here, a flathead or a Phillips head or anything like that, right? Okay, so this is the formula, 2 pi L over P, where P is the distance between the threads or the lead, and L is the radius of the effort that we're applying, right? Okay, so just keep that in mind. And the next one is the pulley. So this is a pulley system, and this is a very famous setup, the block and tackle, where we connect two pulleys and we use it to distribute the load. And as we would always say with velocity ratio, we want to apply a smaller effort over a longer distance and concentrate that to move a bigger load. And that's what this is doing. So what we find is that when we apply the effort for, let's say, 1 meter here, this mass would be raised half meter, because the rope or the cable or whatever it is in this block and tackle one here, this one with just two pulleys, double, right? It's double. So if we pull 2 meters on this rope, here is just going to travel 1 meter up. Yeah, number of pulleys, right? Okay. So for the pulleys, it's the number of pulleys in the system. That's the velocity ratio. For the screw equation, it's this formula here. Now, this picture says ideal mechanical advantage. And we know the ideal mechanical advantage is the same as the velocity ratio. So that's why that's there. And if you were thinking along the lines of when would I ever need to use a pulley? Well, if you are a civil engineer or a mechanical engineer and you want to design the draw system for a bridge so that ships can pass, like in the Marhar Bridge, these systems here employ pulleys along with many other things, right? Pulleys and different cable tensions, and of course this here, we'd have to balance the structure and the weight that pulls down here too, right? So it's not just a pulley, it's a pulley along with a lot of other things. But this is one way we can apply a pulley.
Reading for me here or on
So keeping all of this in mind, let's start working these questions. Okay? Okay. So a screw of a certain screw jack has a lead of 10 millimeters. An effort of 120 newtons is applied tangentially at the end of a bar having a radius of 250 millimeters. The efficiency is 0.3 per unit. Calculate A, the load in kilonewtons, B, the velocity ratio, and C, the mechanical advantage. Okay. So as always, we know we start with a velocity ratio because it's just simpler that way, right? And we just found out that the velocity ratio is 2 pi times L, or R, which is the radius of the effort, divided by the lead of the threads, right? Distance between one thread to another. And in that diagram, it was called P. Right? So putting that into our formula, 2 pi times the radius of the bar that we're applying the effort, which is 250 mm, divided by 10, the distance between the threads in the screw jack. Plugging that into our calculator, we get the velocity ratio as 157.1. Any questions on this? No? Seems simple enough, right? Now, again, before we find the load, we need to move on to the mechanical advantage, and then we can use that to find the load. Okay, so using this velocity ratio that we just found, the 157, and the efficiency, which was given to us as 0.3 per unit or 30%, plugging that into our formula for efficiency. Someone asking something?
Yes, sir. Can you please write the formulas?
Okay, sure.
Thank you.
So the formula for velocity ratio, I'll edit this document and I'll add the formulas on top, which should be easier for you guys. The velocity ratio is 2 pi L or 2 pi R, which would be the radius of the effort, right? Divided by L or P, whichever one you want to put, which is the distance between the threads, right? The distance between the threads. Okay, so that's that first formula. Now here, we know efficiency is equal to the mechanical advantage divided by the velocity ratio. And this is a formula that's in the previous handout. So we should know this by now, right? Efficiency is equal to the mechanical advantage dividing by the velocity ratio. Substituting the efficiency that was given to us as 0.3 per unit and the velocity ratio we just calculated as 157, putting that into the formula, we get 0.3 is equal to the mechanical advantage, our unknown, divided by 157.1. Transposing, we get the mechanical advantage equal to 157.1 times 0.3, and that's equal to 47.13, which is, of course, our mechanical advantage, right? Now, next formula, we want to find the load. And we know mechanical advantage is what we gain out of this system, right? How much additional force were we able to move or oppose in this system? So it's the ratio between the load the load, and the effort we put in. And the effort we put in. So if we applied a small effort and we're able to move a bigger load, then we gain some sort of mechanical advantage. So this effort, of course, again, not to be confused with efficiency. So the effort was given to us at 120 newtons. And we just calculated our mechanical advantage as 47.3. So plugging that into this formula, we get the mechanical advantage, 47.13, is equal to the load divided by the effort, which is 120 newtons. Solving for the load, we get the load is equal to 120 newtons times 47.13, which is equal to a very big number, 5,655.6 newtons, or more simply, 5.7 kilonewtons, right? 5.7 kilonewtons. Any questions overall, generally on this? No? No questions? All right, moving on. Okay, good. So number 11. A screw jack, again a screw jack, is used to lift a mass of 500 kilograms. The lead of the screw is 12 millimeters. Calculate the force required at the end of the 300 millimeter arm, assuming the efficiency to be 28%. Also, determine the velocity ratio and the mechanical advantage. Good. So again, a screw velocity ratio, we know the formula is 2 pi r, which is the radius of the effort, divided by the distance between the threads, or the lead of the thread. Okay. In this case, the lead of the screw is 12 millimeters, and the radius of the effort, or the force required at the end of the arm, is 300 millimeters, right? Substituting that in. 300 millimeters. 12. We had the velocity ratio as 157.1. As 157.1, right? Now, notice we didn't need to convert because velocity ratio is a unitless term and both of them are in millimeters, right? We didn't need to convert into meters. You can if you want to. Okay, good. So with that velocity ratio and with the efficiency that was given to us as 28%, or 0.28 per unit, we get efficiency is equal to mechanical advantage divided by the velocity ratio we just found. Again, transposing, solving for mechanical advantage, we get the mechanical advantage is equal to 157.1 times 0.28, which is equal to 44. So this is our mechanical advantage. Okay, Nicholas, go ahead.
Yes, sir. Yes, sir. How it said 28% efficiency, but why 0.28?
So 28%, yeah, percentage, right? So turn this into a number, not a percent, because percentage is out of 100, right? So essentially this is a fraction, 28 over 100, which you could for sure write down here, or you could just write this down as 0.28, right? 0.28.
Okay, now I understand, sir. I understand.
So when we give it in per unit, they mean as the number per unit, right? The unit values. And when they give them percent, they of course mean a fraction out of 100. Percentage, right? Okay. Okay. So 28.
That's right. That's right.
So we found the mechanical advantage as 44. Good. So using that as 44, we know the mechanical advantage, right, is equal to the load divided by the effort. The effort is what we would want, to find, right? So in this formula, we substitute the load, and the load is this 500 kg mass. Right? A screw jack is used to lift a mass of 500 kgs. And of course, we know that we need to multiply that by 9.81 to get weight, right? Yeah, good. Now, mechanical advantage is equal to 500 kgs times 9.81, right? So the mechanical advantage we of course found is 44, right? So 44 is equal to that same 500 kgs times 9.81 divided by our effort, okay? Yeah. Now, solving this equation for the effort, we of course carry over, bring back, right? Do a little algebra, however you want to do it. And we find the effort being equal to 500 kgs times 9.81, your gravitational constant, divided by 44, which is your mechanical advantage. Plugging all that into a calculator, we get 111.5 newtons as our effort. Okay, good. And that's simple. It's pretty similar to the stuff we did last week in last week's class. It's just that the velocity ratio is changing, but the methodology is the same, and we're doing the same thing again. So, any questions? Okay,
Yes,
John.
sir. Question.
Yep, go ahead.
Yes, sir. The mechanical advantage is equal to 44, right? And I see a 44 equal 500 kg times 9.81 over
Yep.
effort. But then in the next slide, I see the 44 switch with the effort. Why?
Okay, all right. Let's go through it. Okay, so what is mechanical advantage? We know the mechanical advantage is the way we quantify that mechanical advantage, that benefits we get out of the simple machine, right? Because that's what this topic is about. We're classifying simple machines and we're putting into numbers how beneficial these things can be. So mechanical advantage is a ratio between the load and the effort, right? That is what it is in its essence, like bare bones, load divided by effort. So just like last week, as I was saying with the lever, if you were able to put in 2 newtons into the effort and you were able to move a 20 newton load, right? And then you gain something, right? You get some mechanical advantage, right? That's what you get, and that's what the mechanical advantage is. Load divided by effort. Now, we also found last week that the mechanical advantage is related to efficiency, right? Is related to efficiency. Efficiency, right? Not to be confused with effort, right? Let me write it as efficiency. Sorry, like that, right? It's equal to the mechanical advantage divided by the velocity ratio. So this here is a separate formula. Mechanical advantage is related to a machine's efficiency by means of velocity ratio, right? I found this out by saying that efficiency is work we put into the system versus work we get out to the system. And the forces and the distances, velocity ratio is the ratio of the distances and mechanical advantage is the ratio of the forces, and we come up with this equation, right? So you can go over that by yourself. It's in the handout, the one Miss gave, so the textbook essentially, and you can come up with this form. So there's a second form. The mechanical advantage is this, right? With this, what actually is, but it's also related to efficiency by means of the velocity ratio, right? So this is the second formula. So we found velocity ratio, right? So we use it along with efficiency, the 0.28, and we use it to find the mechanical advantage. So we use the efficiency we were given, the 0.28, the 28%, the 0.28, and the mechanical and the velocity ratio we just found, right? 157. Transpose and we find the mechanical advantage is 44. Right? So find the velocity ratio, find the mechanical advantage. Right? We're also asked to calculate the force required. So we know the mechanical advantage is the ratio of these forces, and we were given the load. So we use this second formula here to say that the mechanical advantage, 44, is equal to the load divided by the effort. And the load here is 500 kgs times 9.81 divided by the effort. And of course, we solve this formula here, right? Effort is equal to 500 kgs divided by 44. So we solve this formula here and we get 111.5 newtons. So does this answer your question?
Not fully, sir, but just one quick thing. The reason why I asked, right? Mechanical advantage is equal to the load divided by the effort, right? And remember, effort is what we basically don't know. And effort is being divided by the load. So if we was to make effort the subject of the formula, wouldn't the load have to multiply by the mechanical energy? This is why I asked how come it switch, how come it move around in such a way that the effort is equal to the mechanical energy divided by the load instead of multiplying.
Okay, all right. We had this question last week also. So let me do it back again. Okay, and I think you guys need some practice with algebra, you know, and yeah, you need some practice with algebra. So this is not only going to be applicable to this class, but also math and any other courses that you solving equations with, right? So maybe you can go to khanacademy.com. Let me get this site. khanacademy.org, and you can go here and you can practice algebra and calculus and whatever. I'm pretty sure it'd be very helpful in your maths course. So this is helpful for everyone that feel like they're struggling a bit in math. Check this place out. And I got lots of videos and stuff. All right? Good.
Excuse me, sir.
Yep, go ahead.
Do we have a test on Friday?
I don't know. Again, ask Mrs. Still.
Okay.
Yeah, but you can always prepare for a test. So if there is a test, you're ready. Yeah. Okay, good. So yeah, again, let's say we had some value here. Let's just write this equation, right? Mechanical advantage, some mechanical advantage is equal to some load over some effort, right? Let's replace this with some numbers. Let's say 3 is equal to 6. 6. Why is this not writing? 6. Divided by 2, right? In order to solve this formula in terms of 2, what we need to do is transpose the 2. So it'd be 2 by 3 equal to 6, which we know 2 times 3 is 6, right? And then carry back over this 3. So 2 equals to 6 divided by 3, right? This makes sense. And that's essentially what we're doing. So we're carrying over, we're doing effort times 44. So we're moving this. So it's E times 44, and then we're carrying it back over, right? And that's what we're doing. This.
Yes, sir, I understand that.
So yeah, if you guys feel like, basic math stuff you're not getting, work on it, practice. Because it's going to be necessary in your second year, obviously. And as an engineer, you can't run away from math, right? You're never going to be able to run away from math, especially basic algebra. So work on it. Go to khanacademy.com and do a lot of practice questions, right? Okay. So this here is the screw, and now we're moving on to the block and tackle, the pulley, right? And again, we know the velocity ratio is based on the number of pulleys within the system, right? And because the rope is be doubling up and tripling up, and it's based on a number of pulleys in the system. Okay, so let's look at number 12. A lifting tackle consists of 2 pulley blocks. Each block has 2 pulleys, right? 2 pulley blocks. Each block has 2 pulleys. One end of the cord is attached to the upper pulley block. Calculate the velocity ratio. B, the effort required to lift a mass of 120 kgs, assuming the efficiency to be 85%, and C, the mechanical advantage, right? So they say 2 pulley blocks, and they say one end of the cord is attached to the upper pulley block, right? So they're telling us how the system is set up, and they're saying that one pulley is here, right? And another pulley is here. And they're saying the rope comes like this, it goes like this, and it's attached back to this other one, right? And of course, there are 2 pulley blocks within the system, and it's connected up. So what they're hinting to us is that the velocity ratio is equal to the number of pulleys. So that's what we put down. So 2 blocks at 2 pulleys each, right? 2 pulleys each. So 2 by 2 is 4. So the number of pulleys in the system is equal to the velocity ratio. And that's it. That's simple. That's as easy as it gets for the pulley. The number of pulleys within the system, that's the velocity ratio. All right. So now, from this, we know from the velocity ratio, we can calculate mechanical advantage, we can calculate effort, efficiency, all these things, right? So keeping this in mind, the velocity ratio is 4. Let's find the mechanical advantage. So again, remember, efficiency is equal to mechanical advantage divided by velocity ratio. Efficiency was given to us as 85%. 85% is 0.85 per unit, or 0.85 as a decimal instead of a percentage, right? So 0.85 is equal to the mechanical advantage divided by 4, which is the velocity ratio. Solving for the mechanical advantage, we get the mechanical advantage is equal to 0.85 times 4, which is equal to 3.4. 3.4, and this is the mechanical advantage. Now, using the mechanical advantage by means of the load, with the load was given to us. The effort required to lift a mass of 120 kgs. And we, of course, need to multiply that by the gravitational constant. So we get 3.4. The mechanical advantage is equal to the load divided by the effort. So the load is 120 kgs times 9.81, right? Okay. Solving for the effort in this formula, we get the effort is equal to 120 kgs times 9.81 divided by 3.4, which is, of course, equal to 346.235 newtons. Just plug this into a calculator and you get 346.235 newtons. And that's it. Boom. Question's finished. Right? We've solved everything. We found the velocity ratio. That's just the number of pulleys. The effort required, which we just find the mechanical advantage first, and then put that into the formula with the load and find the load. So any questions on this? Simple is the pulley. The only difference is the velocity ratio, which is the number of pulleys. No. All right. So hopefully when you guys work number 13 by yourselves, maybe then you'll find some questions. Okay. So let's look at number 13. System of pulleys consists of an upper block fitted with 3 pulleys, right? And the lower block fitted with 2 pulleys. An effort of 240 newtons is required to raise a body having a mass of 85 kgs. Calculate A, the velocity ratio, B, the mechanical advantage, C, the efficiency, and I'll work D and E with you guys, right? But A, B, and C is where you guys need to work, right? So yeah, C, the efficiency, D, the work done in lifting the body 50 millimeters, and E, the corresponding work done by the effort. So take 7 minutes or 10 minutes, work this question out, and let's all see if we get the same answers, or if we find any difficulties, then we can help each other out, right? Okay. So work these questions and tell me what answers you get. Yeah.
I was asking if I could work it on the board, on the whiteboard.
Yeah, you could. All right.
Right now?
Your voice is very low.
Oh, I was asking if I could work it on the board right now.
Okay, yeah, but let's give everyone 5 minutes, let they work it first, and then we'll come to you. All right, and then you could work it on.
Oh, okay.
Okay.
Excuse me, sir.
Was someone asking something?
Yes, sir. Can you do you have the formulas anywhere down there?
Okay.
The formulas, like
Sure.
the mechanical advantage formula.
So let me just
Yes, sir.
let me put them up.
Yes, sir. I just want to screenshot it quickly.
I'm up. These are very simple formulas. You guys should know them out your head by now, right? Open up. All right, good. Mechanical advantage, load divided by effort, velocity ratio. Right?
Yes, sir. Thank you very much.
Let me see if I can copy and paste it. Maybe. Yeah, tell me when you guys finish. And we look at it over
Yes, I
together.
finished, sir.
Finish. Who's that? Let me see. Jamal. All right. What answer
Yes,
you
I
got, Jamal?
finished.
What answer you got for the velocity ratio?
Okay, sir. What about Swedish? Sorry, it's 5.
Okay, so the velocity ratio is 5. Good. Very good. What's the mechanical advantage?
Okay, so right. So mechanical advantage is equal to the load over the force, right?
Just give me the answer. Right?
Okay, sir.
Everyone's working it,
Thank you.
so give other
So I get 3.5.
3.5. Okay. And
It's 3
efficiency?
point. Yes, sir. It was 3.474, but I rounded up to 5.
Okay,
That one
good.
knows no place.
And what was the efficiency?
Efficiency, sir?
Yeah.
Sir, 0.7.
Okay. 0.7. Let me see. Mhm.
So one question, sir.
Yeah, go ahead.
Okay, sir. For D, right? I
Mhm.
know that we use the force as the effort, right? To find for the mechanical advantage, right, sir?
Mhm.
Okay, great.
For B,
So
yeah.
when find so work, right? Work will equal up to force times distance, right?
Yes. Okay.
Seeing that we know the mechanical advantage
Mhm.
and the weight, we could find for the force.
Mm. Okay. So the work done in lifting the body 50 millimeters, right? So the body is 85 kilograms. Yeah. Good. And we're moving that 50 millimeters. Right? So it's just simply work. It's just simply work, right? Is equal to the force times the distance, right? Or the weight of the body times the distance. So force times distance, right? Okay. So the work is 50 millimeters times this as a force, right? As weight, so 85 kgs times 9.81, right? So for find the work, you don't really need to use the mechanical advantage, right? If you have what I'm saying.
Okay.
But to find the corresponding work done by the effort, right? You want to use efficiency. Yeah, for this part, you want to use efficiency.
So you have to divide the effort by the efficiency.
You'll have to divide, okay, so efficiency is equal to work done by load. So work done on load. Yep. Divided by work done by effort, right? right? And then scroll. So this is what you want to use.
Yes, sir. So the work, right? The work done by the load.
Yeah,
Um,
good.
I
So
will assume that
what is the load? What is the load in this case? This 85
the load
kg mass.
85. Yes, is that sir?
Good. So if we're lifting it 50 millimeters, how much work are we doing? We're moving this body 50 millimeters, and to move that body, we need to oppose its weight, right? 85 kgs times 9.81 for 50 millimeters, right? So that's what we're doing to find the work. Does that make sense?
Yes, sir.
Good. And then we use efficiency because we know the work we get out of the system, the useful work done on load, is related to the work we put in the system by the effort, by means of efficiency, right? So efficiency is like what percentage of this work on load is coming from this effort, like, and what's going to losses. That's kind of what efficiency is. Yeah.
So looking at the formula, so right, we know the efficiency, right?
Yeah. Do we know it?
Okay. We know the,
Yeah, good. We calculated it.
we know. Yes, we know efficiency, and we do the work of the load.
Mm-hmm.
So I have to just find the work of effort.
Yeah, good. So how do you do that?
Well, the work of the load will be divided by the efficiency to find the work for the effort.
Mm-hmm.
Let
Good.
me just calculate.
Good.
Excuse me, sir. So when for finding the efficiency, right, it's not I think is
Velocity
is
ratio.
velocity. Yeah, it for find is the mechanical advantage over velocity ratio, right?
Yeah, this formula.
Okay. So now when you got to find where's the next one for find the is what
The work
that thing
done.
is he asking for? The work done. Yeah,
Yeah.
the work done.
Yeah.
There's the workload over the work effort, right?
Yeah. For this part here. So we found efficiency, right? And now we're using it to find corresponding work done by the effort. Right? Now there are many ways to do this. This is just the simplest one, right? Yeah, this is just the simplest one. Yeah. Okay, so I guess enough people's finished, and who wanted to work the question on the board? Steve?
Yes, sir. I
Funding.
wanted to work the question.
Okay.
Excuse me, sir. So for the corresponding work done, sorry for the service, sir. So
Yes.
the corresponding work done by effort. How we
Yeah.
solving that?
So first we're finding the work done in lifting the load, right? The useful work done in lifting the load, and then we're using efficiency to find the work done by the effort. So this formula is basic, right? Again from last week. It's not one that you would write down, but it's one that essentially is what efficiency is, right? It's work we get out of the system divided by work that we put into the system, right? Maybe I should give you guys that form. But the thing is, with giving you guys formulas is that you don't really understand what the concept is as opposed to me just giving you the formula. So efficiency, like as I was talking about this last week, efficiency is equal to the work we put into the system as a ratio of the work we get out of the system. So it's telling us how much are we losing to friction and things like that. No losses. If it's 85% efficient, right? And let's say we put 100 newtons into the system, that means only 85 newtons or 85 newtons, assuming they both travel the same distance, right? Assuming they both travel the same distance, it means only 85 newtons is being used to move the load, yeah? Or let's say in terms of work, we put 100 joules into the system and efficiency is 85%, that means only 85 joules is being used to raise the load. And the rest of the joules, the rest of the energy is going to losses, things like friction. Right? That's what efficiency is. So it's the work done on the load divided by the work done by the effort. Okay. Okay. All right, Steve. Right to work question.
Yes, sir. I have to write on the board, or I tell you what to write.
I'm not hearing you very well.
Oh, I was asking if I have to tell you what to write, or if I have to write.
No, you can go ahead and write, Steve. Yeah, good.
So, first you write down the values they gave. They gave you 3 pulleys up the block.
Turn on annotations. Yeah, can you annotate now, Steve?
Oh, you cannot see what I'm writing on the board?
What color are you writing in? White?
Blue.
Okay, yeah, okay, good.
Yeah, okay. Then you have 2 pulleys in the low block. Right, and velocity ratio is equal to the number of pulleys that you have. So it would be 3 plus 2
Okay.
would give you a velocity ratio of 5, right? And
Okay.
then they also give you which is 240.
Steve, can you speak up?
Yes, Steve.
Well, I'm actually
Okay, Steve, let me work it because that would be better since no one can hear you. All right.
good.
Let me work it. All right. Good. So hopefully you guys can hear me better than you can hear Steve. Right? Okay, good. So what he was saying is that using that same thing that we figured out, that the velocity ratio is equal to the number of pulleys in the system. And this system consists of an upper block and a lower block, right? A system of pulleys consists of an upper block fitted with 3 pulleys and a lower block fitted with 2 pulleys. So what that tells us is that the velocity ratio, let me type. Yeah, so what that tells us is that the velocity ratio is equal to the number of pulleys in the upper block 3 plus the number of pulleys in the lower block 2, which is 5, which is the total number of pulleys in the system. So most of you got that right, that's 5. Next, the mechanical advantage. Well, how do we find that? We found velocity ratio, right? Oh, actually they didn't give us efficiency, so we just need like regular mechanical advantage. So we know the formula for the mechanical advantage is equal to the load divided by the effort which is equal to, and they gave us the values, right? They gave us the effort as 240 newtons, and they gave us the load as 85 kgs. And of course, we're going to need to multiply that 85 kgs by 9.81, right? So 85 times 9.81 divided by the effort, which is given to us as 240 newtons. And plugging this into our calculator, we should get 3.47. So 85 times 9.81 divided by 240, 3.47. And this is the mechanical advantage, which is what, again, what most of you got. Or I think just 2 of you submitted your answers. So the next part, the efficiency. So we know, again, efficiency is equal to mechanical advantage divided by velocity ratio here. So the mechanical advantage is 3.47. Efficiency, let's just write it as this fancy E thing, because we don't want to mix it up with effort writing EF. Right, so efficiency is equal to mechanical advantage 3.47 divided by our velocity ratio, which we found as 5. Plugging this into our calculators, we get efficiency as 0.694, or as a percentage, we can just say 69%. Cool. 69%, which is great. And again, that's what these two guys got. 0.7, he rounded up. 0.69, he didn't round up. Again, so 69%. So we found the first three, A, B, C. Now, the work done in lifting a body, 50 meters. Now, we know what body we're lifting, right? They told us we're lifting this 85 kilogram body. So the work done to lift that body, right? Work done to lift that body is equal to 85 times 9.81 Okay, Jamal, go ahead.
Yes, I got one question, sir. So we must always like keep our answer at 2 decimal place?
It depends. Depends. Yeah.
Okay.
You should 0.69. I do because it's more precise. Yeah. It's more precise, and rounding can lead to problems, especially in really complicated systems. You know, you don't want to round up a lot of forces, and next thing you know, the building you design fall down because you round up too much. Yeah. So yeah, maybe try to be more precise. 2 decimal places is fine. It all depends on the application. Yeah. This is just a question for class, so rounding doesn't really have that much value. But when you go into the world of work and you start designing systems, or maybe you're doing your own project, you know, your second year project or your final year project, rounding might have more value then. So you might want to keep your decimal places. Yeah. I think there was an error with a space mission where just rounding the wrong value caused the buffer overflow, and it just caused the airship to not go up or not launch. Yeah. So yeah, try not to round too much. So yeah, 85 times 9.81 times. So this here is the force, right? Obviously. Times the distance we travel, which is 50 millimeters. 50 millimeters. 50 millimeters is 0.05 meters. Yeah. So this here, multiplying it out. Let me multiply it out real quick. 5 times 9.81 times 0.05. This should give us 41.69 joules. Yeah, joules. Because work. Good. Now, for the corresponding work done by the effort. Now, we don't know what distance the effort traveled, and could maybe find it using velocity ratio and translating this and doing all sorts of other things and applying the effort. But simply, since we have efficiency, and we know efficiency is equal to the work done on the load divided by the work done by the effort. So the work done on the load is 41.69. 0.69 divided by the work done by the effort. So this is work. Let's call this work 1. Let's call this work. And let's call this work 2. And efficiency we know as being 69% or 0.69. 0.69. Okay. Now transposing finding for work, we get work is equal to this 41.69 carry over, bring back, divided by the 0.69, right? So 41.69 divided by 0.69. Let's plug that into our calculators. Is equal to 60.42 joules. 60.42 joules. So this is it. These are all your answers. I'll neaten this up and put it into the handout so you guys can access it easily. But
Yes, I got one question, sir.
good, go ahead.
Right? I think I asked it previously, but remember that we remember that the effort is also a force, right, sir?
Yeah.
Okay, good. Right. Since that we use the effort, since mechanical advantage is equal load, right,
Yeah.
over the force, but we could use the force as an effort, right? But I want to know, like, why did we use the why didn't we use the effort like to find the work as the force? That is why I get a little confused.
Okay, let me see. Well, it's because we don't really know the distance traveled by the effort. Yeah. What's the distance traveled by the effort? Because if we're going to just use 240 newtons, we're going to need to know the distance traveled by the effort, right? So what is it?
Yeah, well, we know it, sir.
Okay, so, I mean, maybe you can find it. How would you go about finding it?
I'm gonna go find it. Let me see.
Yeah.
I have no idea. I know if you could help me that.
So what is velocity ratio? Distance moved by effort divided by distance moved by load?
Yes.
So you think you
Okay.
can find it?
Wait. We could use that same formula
Try.
to find the distance moved by effort.
Yeah, try and you tell me. Yep. It should work out. Take a few seconds, do it. Or you want me to do it for you?
No, I just want just pull about. Yes, let's leave it right there. I'll work it out.
Hmm.
So the first ratio is going to be 5,
Hmm.
right? Distance moved by the load.
0.05.
That'll be yes.
Yeah.
So we'll have to multiply 5
Mhm.
times 0.05.
Yeah.
0.25.
Yep. And then multiply that by 240. So this here is equal to 0.25.
60.
Okay, good. And what answer did we get?
60.
Does it work? What do you think? Is it good? Does it work? Yeah.
Well, it close enough, yes, I could say. Very
Yeah,
close.
good. It works. It works. It's just, we rounded up a little bit here. 0.694, little rounding errors here and there. But yeah, it works. Right? It works.
Yeah.
Good. So I hope you guys learned something today. And that's all I have for you. I'll put the working in here, but this one I'll type it out neatly so you guys can look at it. All right. So that's all I have for you.
Thanks, sir.
If there aren't any more questions, enjoy the rest of your day. Right?
Same to you, sir.
Thanks, sir. Same to you.
Good.
Yeah, thank you very much, sir.